In this video, we're going to look at how we can use vectors to describe the equation of a plane in three-dimensional space. We're going to start by considering an example and seeing that there are two different ways of representing a plane. So we're going to consider the plane which contains the 3 points A with coordinates 4, 1, 2, B with coordinates 3, 5, 3, and C with coordinates -2, 1, 3. And we'll represent this in a schematic diagram again. So on the diagram we've got the origin marked, and we've got the plane together with the points A, B and C on the plane. And we've also marked on a general point P on the plane. So if P is an arbitrary point on the plane and R denotes the position vector of P, so that is the vector O to P, then we can say that the movement from O to P is the same thing as, first of all, the movement from O to A, so that's to get me onto the plane, and then a movement from A to P, which is a movement across the plane. Now, if we look at the diagram and concentrate on the plane for a moment or two, then the vector A to B lies on the plane, and we've also got the vector AC lying in the plane. Now, in moving from A to P, we can break that down into a movement along the line AB, followed by a movement parallel to the line AC. So we can say that the movement from A to P is a multiple of AB plus some other multiple of AC. So that now means that we can write the position vector of the point P. So we can write R as OA, that's onto the plane, plus a movement in the direction AB. So that's the part we've got S times the vector AB. And then finally a movement along a vector which is parallel to AC, and that's the movement T times AC. So we've got the equation is R, the position vector of P, is OA plus S times AB plus T times the movement AC. Now the vector OA is the vector 4, 1, 2. The vector AB is the movement -1, 4, 1. And the movement A to C is the movement -6, 0, 1. So what we've got is R is 4, 1, 2. That's the movement from the origin to the point A, plus S times -1, 4, 1. So that's the movement along AB, but further than B, as in this diagram. And then finally, we've got the movement parallel to AC, which is T times -6, 0, 1. And in general, if we've got A as a point on a plane, and U and V are two non-zero, non-parallel vectors lying on the plane, then if P is an arbitrary point on the plane, then we can write the position vector of P, that is R, as being A plus S times U plus T times V. Now we would call this the vector equation of the plane. Now we're now going to try and find the Cartesian equation of the plane. Now if you've got a plane, there's going to be a vector which we're going to call n, and this vector n is perpendicular to the plane. And if it's perpendicular to the plane, it certainly means that it is at right angles perpendicular to all vectors that lie on the plane. So this vector n is certainly going to be perpendicular to AB, and it's also going to be perpendicular to AC. Now we can use that to find out what this perpendicular vector is. So if we say let n be the vector alpha, beta, gamma, then we've got alpha, beta, gamma is perpendicular to AB, and AB is the vector -1, 4, 1. So we've got also that alpha, beta, gamma has got to be perpendicular to AC. So that means that we've got alpha, beta, gamma dot -6, 0, 1 must be equal to 0. Taking the dot products gives us two equations. It gives us minus alpha plus 4 beta plus gamma must equal 0, but also minus 6 alpha plus gamma must equal 0. The second of these two equations tells me that gamma must be equal to 6 alpha. And if we insert this into the first of the two equations, we've got minus alpha plus 4 beta plus 6 alpha must equal 0. In other words, we've got 5 alpha plus 4 beta equals 0, so beta is minus 5 alpha divided by 4. In order to get integer values in our vector n, it might be sensible to set alpha up as being 4, in which case we get n is alpha, which is 4, beta, which will be minus 5 times 4 divided by 4, which is minus 5, and gamma, which is 6 times alpha, which is 24. So we've got a normal for our plane, which is the vector 4, minus 5, 24. So there's our normal sitting on the diagram of our plane. Now we know that the normal is perpendicular to all vectors on the plane. In particular, it's going to be perpendicular to the vector AP. So we know that the scalar product of AP with n must be equal to 0. Now AP is the movement from A to P, which can be written as being from A to O, which is minus little vector A, plus the movement from O to P, which is plus the vector R. So I've got minus A plus R dot n must equal 0. Multiplying the brackets out, we've got minus A dot n plus R dot n must equal 0. Or in other words, we've got R dot n must equal A dot n. So the value of A dot n is easy enough to work out. We know A is the point 412, so the vector little a is the vector 412. We know that n is 4 minus 5, 24. So doing the dot product, we've got 4 times 4 is 16, plus 1 times minus 5, which is 16 plus minus 5 is 11, plus 2 times 24 gives me 59. So what I know is that for all points on the plane, the value of r dot n must be equal to 59. And that's true for every single point on the plane. Now r is the position vector of our general point P. So if the coordinates of P are x, y, z, then the vector r is just the vector x, y, z. So we've got x, y, z dot the normal, 4 minus 5, 24 must equal 59. In other words, we've got 4x minus 5y plus 24z equals 59. And this is the Cartesian equation of the plane. So, just to summarise, we've said the plane has got a vector equation, r equals 4, 1, 2, plus s times minus 1, 4, 1, plus t times minus 6, 0, 1. And then we said that the plane has got a Cartesian equation of the form 4x minus 5y plus 24z equals 59, which came from the fact that r dot n was equal to a dot n for all points on the plane. Now we can generalise the work that we've done so far during the course of this video to obtain two important results. First one is that if we've got the plane passing through the points A, B and C, then the plane has a vector equation of r, that's the position vector of a general point on the plane, is equal to OA plus S times AB plus t times the vector AC. And that's fine provided the vectors AB and AC are not parallel to each other. If we can find the normal vector for the plane, and r is the position vector of our general point on the plane, then we observed that the value of r dot n is the same for all points on the plane. And that means that the equation of the plane can be written in the form either r dot n equals a constant, or xyz dot n1, n2, n3 equals the constant, or, if you like, n1 times x plus n2 times y plus n3 times z equals a constant. The value of the constant can be found provided we know a point which lies on the plane. And the equation n1x plus n2y plus n3z equals that constant is called the Cartesian equation of the plane. So, let's have a look at some examples. First of all, we've got to find the Cartesian equation of the plane which passes through the point A with coordinates 5, 1, 2 and has normal 2i plus 5j minus 3k. So, we know that the equation of the plane is of the form r dot n equals a constant. So in this case we've got r dot 2, 5 minus 3 must equal a constant. The value of the constant can be found using the point 5, 1, 2. So the value of the constant must be whatever the scalar product 5, 1, 2 dot 2, 5 minus 3 evaluates to. And this gives us 10 plus 5 plus minus 6, which gives 9. So the equation of the plane can be written as r dot 2, 5 minus 3 equals 9, or xyz dot 2, 5 minus 3 equals 9, or 2x plus 5y minus 3z equals 9. Since the question asks for the Cartesian equation, we really ought to be giving the answer in that final form, 2x plus 5y minus 3z equals 9. In the second part of this example, we're asked to find the Cartesian equation of the plane which contains the points 1, 0, 0, 3, 1, 2 and 2, 5, minus 2. It's worth just drawing a very quick sketch diagram. With the sketch diagram now, we can see that the plane contains the vector st, and the vector st is 2, 1, 2. And it also contains the vector su, and su is the vector 1, 5, minus 2. The normal must be perpendicular to both of these two vectors. So we are looking for a vector we'll call it alpha, beta, gamma, which is perpendicular to 2, 1, 2, and also perpendicular to 1, 5, minus 2. So we've got alpha, beta, gamma dot 2, 1, 2 must equal 0. Gives me 2 alpha plus beta plus 2 gamma equals 0. We've also got alpha, beta, gamma dot 1, 5 minus 2 equals 0. And that gives me alpha plus 5 beta minus 2 gamma equals 0. If we rearrange those to get the gammas on the right hand side, we've got 2 alpha plus beta equals minus 2 gamma as our first equation. Alpha plus 5 beta equals 2 gamma for my second equation. And we can eliminate the alphas pretty easily by taking the second equation and taking twice the second equation and subtracting the first equation. So taking the second equation, times it, multiplying it by 2 and subtracting the first equation. First of all, got 2 lots of alpha, take away 2 alpha, so that's no alphas. I've then got 2 lots of 5 beta, take away beta, which is 9 beta. So I've got 9 beta on the left hand side, and on the right hand side I've got 2 lots of 2 gamma, take away minus 2 gamma, so that gives me 6 gamma. So I've got 9 beta equals 6 gamma, which means that beta must be 2/3 gamma. And if I insert that back into equation 2, I get alpha plus 10 over 3 gamma must equal 2 gamma, which means that alpha must be minus 4 over 3 gamma. To get nice integer values for alpha, beta and gamma, it would seem sensible to choose gamma equals 3, in which case we've got alpha is minus 4, beta is 2, and gamma is 3. So we've got a normal of minus 4, 2, 3. So having revised our diagram to show that the normal is minus 4, 2, 3, we now know that the equation of the plane must be r dot n equals a constant. So the equation of the plane must be r dot minus 4, 2, 3 equals a constant. We know that the point 1, 0, 0 is on the plane, so the value of the constant must be 1, 0, 0 dot minus 4, 2, 3, which gives me minus 4. So the equation of the plane is r dot minus 4, 2, 3 equals minus 4. And if we just think of r as being the position vector of our arbitrary point, so r is the vector x, y, z, then that gives me minus 4x plus 2y plus 3z equals minus 4. Now in our second example, we're going to consider the intersection of a plane and a line. So first of all, we're going to find the equation of the plane which passes through the point 525 and which has a normal of 3, 5, minus 2. Well, the fact it's got a normal of 3, 5, minus 2 means I know the equation of the plane is r dot 3, 5, minus 2 equals a constant. I know the point 525 is on the plane, so the value of the constant can be found by just evaluating 525 dot 35 minus 2, and 525 dot 35 minus 2 is 15 plus 10 minus 10, which just gives me 15. So the value of the constant is 15. So the equation of the plane is r dot 35 minus 2 equals 15, or 3x plus 5y minus 2z equals 15. The vector joining B to C is the vector 2, minus 3, 2, and that provides a direction vector for our line. So we can say that the equation of the line is going to be move on to the line at B plus S or T times by a direction vector for the line. So we've got the equation of the line is R equals -2, 15, -12 plus T times 2, -3, 2. So we now want to find the point of intersection of the two. And for a point of intersection, we're going to have to solve some simultaneous equations. So we've got the equation r dot 35 minus 2 equals 15, and then we've got the line equation r equals -2, 15, -12 plus t times 2 -3, 2. Now it's quite convenient to rewrite the line equation just in the form r equals -2 plus 2t, 15 -3t, -12 plus 2t, because we can then substitute that straight into the plane equation to give -2 plus 2t, 15 -3t, -12 plus 2t, dot 3, 5 minus 2 equals 15. So that means I've got 3 lots of -2 plus 2t, plus 5 lots of 15 -3t, plus -2 lots of -12 plus 2t, must equal 15. And that simplifies to 93 minus 13t equals 15. Or in other words, we've got 78 equals 13t, so t must equal 6. Now if t equals 6, if we use the line equation, we've got the point on the line is given by -2 plus 2t, which gives me 10, 15 minus 3t, which gives me 6, and -12 plus 2t, which gives me 0. So we've got the position vector of the point of intersection is 10, -3, 0, which means that the point of intersection is the point 10, -3, 0. And our final example, we want to find the intersection between the plane 3x plus y minus z equals 11 and the line x minus k over 2 equals y plus 1 over minus 3 equals z minus 3 over 3. In the cases where k equals 5 and k equals 7, and we just want to interpret the solutions geometrically. So the plane has got an equation of r dot 3, 1, minus 1 equals 11. And we want the vector format for the equation of the line as well. So the vector format for the line is going to be r equals k minus 1, 3, plus t times 2 minus 3, 3. We saw how to move from the Cartesian equation of a line to the vector equation of a line in the last video. So to find the point of intersection, we need to solve those two equations simultaneously. Rewrite the line equation in the form r equals k plus 2t minus 1 minus 3t, 3 plus 3t. And then substitute for r into the plane equation, gives me k plus 2t minus 1 minus 3t, 3 plus 3t, dot 3, 1 minus 1 equals 11. So I've got 3 times k plus 2t plus 1 times minus 1 minus 3t plus minus 1 times 3 plus 3t equals 11. And that simplifies through to 3k minus 4 plus 0t equals 11. Now let's have a look now at the two cases separately. If we have k equals 5, then this simplifies to 11 plus 0t equals 11. And that is true for absolutely any value of t. And what that means is that the whole of the line L, if k equals 5, is actually on the plane. On the other hand, if k equals 7, then the equation 3k minus 4 plus 0t equals 11 becomes 17 plus 0t equals 11. And that, of course, is impossible. We can't have 17 equaling 11. So that equation is impossible. It has no solutions at all, which means that the line doesn't intersect the plane at all, which means that the line must be parallel to the plane. To finish off this video, there's a couple of questions here for you to have a go at. So again, as you've done in previous videos, pause the video and have a go at these questions. And that will then conclude our work looking at the equation of a plane in 3 dimensions.